Yeah, thanks for the opportunity to talk here. This is another work in progress I'm doing. I'm in my last year of my PhD at ASU, and my advisor is Dr. Walker. So, kind of to motivate this, I think one of the central questions that I want to talk about is considering how much our choice of reference machines matter. I think we all probably believe this is a surmountable problem because we work on these things. But I think some of the arguments that are given for this can be a bit touchy and they don't always apply in every case. And so I think there's two really common uh, sets of arguments that you'll get, and I want to talk about both of them briefly. So the first is coming from these invariance theorems, right? Where since the language reference machines we're using are universal, they can emulate one another. And so the size of that program sets some constant by which these languages can differ in their Kolmogorov complexity or in their like universal distribution weights. But then there's another class of explanations given that are something about, that we can make a reasonable choice of reference machine. And I think this one's much more blurry. I think people mean a lot of different things when they say this. I think sometimes they mean that, they're not shunting the complexity of their problem into the language. But other times I think they mean things about, how simple the machine is and if it's like something that's easy to physically instantiate and somehow that's less biased in a really general way. And so I'll come to both of these explanations in turn. So first, I want to say that for these invariance theorem sort of explanations, we're often working quite far from this asymptotic regime. And so I think to illustrate that, I think it helps to look at some concrete examples. So like if we want to write a BF emulator in C, the shortest one, at least that I can find, is code gulfed down to just under 1300 bits in size. And so, you know, thinkably people could do better, but I think it's safe to say that the size of this prefix is roughly on the order of 10 to the 3 bits, around 1,000 bits. But if we want to do, resource-bounded estimates of AIT quantities like Kolmogorov complexity or the universal distribution, we're typically only making it out to tens of bits in program length. And like earlier this week, Monday afternoon, Luan Ozalim spoke about this language called F, which is like a restricted version of BF and only has 5 commands. And there they estimated the universal distribution out to programs whose length was about 30 bits. In the case of that language, I think it was like 13 characters, I want to say. But of course, there's a big gap between these two, and it's hard to actually make these invariance theorems do any work here, right? So like on this left side, this like canonical version of it, I guess, right? These Kolmogorov complexities we're dealing with or estimating numerically, these are going to be on the orders of tens of bits, and this constant is going to be on the order of, I can pull up a laser pointer. Yeah, there. This is going to be on the order of 1,000 bits, right? And so this is really not a constraint at all. And likewise, if we're thinking about universal distributions, here we're, getting these distributions estimated down to a factor of, say, 1 part in 2 to the negative 30 or so. But this constraint is only in a multiplicative factor of like 2 to the negative 1,000, right? And so it's really not much of a constraint at all. These two things aren't really making contact with one another. And so it's hard to know, suppose we were wrong and these things are really different from one another. We wouldn't actually be making those observations empirically necessarily. So that brings me to, I think, the second class of descriptions, which I'm going to focus on a bit more in this talk. And that's, these statements about whether languages are reasonable. And if you try to think about ways you might try to show that, it's rather hard, especially if you're coming from a strictly mathematical point of reference. So if you try to make some like cardinality arguments that maybe, languages with strange properties are really infrequent and we just want like the normal ones or something like this. These sorts of arguments tend to break down, right? So if I give you any sort of finite in-out behavior specification, which an observer might have or demand, there's a countably infinite set of distinct, additively optimal universal Turing machines that can meet those specifications. And if you're really clever, you'll maybe think to look for a stationary distribution over different reference machines. So this is a paper from like 15 years ago at this point, where this guy, Marcus Muller, he takes the network of all binary universal Turing machines emulating one another with these like emulation prefixes tying them together, right? And he asks, is there a stationary distribution on this space? And for several reasons, there isn't. And he comes to the conclusion that, this sort of task of trying to find some privileged reference machine or class of reference machines is not possible via strictly mathematical methods. And so it's kind of analogous to like a no free lunch theorem, where what we need to do is incorporate some knowledge of the physical world or the specific problems we're dealing with to sort of break that degeneracy. And so that brings us to what I think is like really the core question. I think is something I'm very interested in, is how can we better relate these reference machines to the physical world? Like in some sense, in the mathematical sense of the word, like constructivism and that movement, the theory of classical computation is constructive, but in the spirit of it, it's not quite constructive enough. And so I think there's lots of ways to attack this problem, but one I want to talk about today is how we can maybe make more interpretable reference machines. And I know that's kind of an overloaded term in this context, but I'm meaning ones where we can give some semantics to them about the systems we're describing. And I'll kind of try to illustrate that a bit better. So I think we can take a lot of lessons from some sub-universal settings. So there's a lot of, and this is kind of my background where I'm coming from, but there's a lot of different scenarios where people want to assign descriptive complexity to things for one reason or another. And effectively, what people are doing in almost every case is they're doing some version of AIT, but with sub-universal reference machines. And when you set out to do something like this, you're faced with very similar questions. If you're trying to like apply AIT directly to other systems, you have to make a choice about how you're going to represent and encode your data, and you have to choose what your reference machine is going to be. And so in these cases, a lot of times what you should imagine, the thing that's playing the role of the reference machine is like a decompression algorithm, right? If you're trying to use like a compression algorithm for complexity measures. And so some maybe example problem you might try to attack with this sort of method is maybe you want to estimate how hard it is to synthesize different chemical compounds. You want some quick and dirty way to do that on the cheap for any given chemical compound, and you want to use molecular complexity as some sort of benchmark for that. So we can walk through a sequence of like improving examples where the semantics gets better and talk through kind of how that works. So I guess the first method I want to talk about, and this is probably like the simplest thing you could do, the easiest thing to do, is represent your molecules as SMILE strings. So this is a canonical data format in like bioinformatics. So basically how you build this for this string or for this molecule here, this string down below is a SMILE string that represents it. So what you would do is you break these cycles, kind of tag where you break them, and then you walk your way down some backbone recursively enumerating these different pieces here. So you can see in this case, you're starting at this green edge and you get to this kind of teal bit, and you can enumerate down any molecule this way, roughly. So you can start with that data representation and then maybe throw it in some LZ compressor. And in that case, the LZ decompressor is playing the role of this reference machine, and the size of the compressed SMILE string is your K analog. So that's like the easiest thing to do, but maybe we can do a little bit better. Even if we still use SMILE strings, maybe we can use, instead of LZ, we might choose to restrict ourselves to some class of CFGs which generates strictly valid SMILE strings, at least syntactically. And so in that case, our K analog is the size of the smallest CFG, which is generating those strings. But this has the added benefit that there's some sort of like extensional semantics. Like the things that can be expressed by this sort of reference machine are strictly those valid SMILE strings. So insofar as this SMILE string paradigm is faithful to what chemical compounds are, right? We're always expressing things that are physically plausible. But I think we can do a little bit better, right? I think maybe I'm kind of hinting at that with this extensional semantics, that maybe we can have an intentional one. And so there, what I would want to think about is maybe a different way to represent these compounds. And so we might represent them with colored graphs. So capturing the kind of natively that graphical description, I guess at the top here, capturing this description. So if we do that, we can let the reference machine be or execute some context sensitive grammars that closely match chemical reactions. So there's a really nice line of research led by people like Christoph Flom and Peter Stadler and others, like Christoph Anderson, where they have these effectively these context sensitive grammars that map onto chemical reactions incredibly well. And they're working on these colored graphs and they're using them for like synthesis planning. And so when you use this sort of complexity measure, effectively what K's analog is it's for a given compound, it's like the size of this grammar is like the number of chemical reactions it takes to build whatever compound from whatever starting set of compounds you may start from. There's some caveats with like exactly how to tie this to K because maybe there's different, you need different amounts of information to encode these different reactions. And so you can put a little logarithmic correction on that. But in general, this has then like an intentional semantics, right? So the computations, not only are you making valid, at least looking molecular graphs that correspond to some plausible physical structure, but the computations that lead to them correspond to things we recognize as a series of physical events. So we've moved up the Chomsky hierarchy a little bit, right? So we're in context sensitive grammars here, but we're not quite at like a universally expressive system. And I think that's like quite a challenge is moving these up to a universal setting. And this is some place where I would love to hear people's ideas if they have some about maybe it's just about finding the right sort of example system. Of course, it's easy to like have some trivial example where the system is describing itself or something, but that's kind of the state of this work right now. And I guess to kind of try to wrap up. So I think this dependence of AIT metrics on the choice of reference machine is a deep problem. And it really seems that there's not a strictly mathematical solution to this. And instead, we have to think carefully about how to associate these machines with the physical world in some fashion. And that the semantics of these machines is one promising avenue at getting at that. And with that, I'll say thank you.